Thanks to the organizers for accommodating me today. There was a little bit of confusion getting here. I'm going to talk a little bit about our new twist on nature's oldest drug carrier, and that's our albumin and fusion technology. I'll talk a little bit about the mechanism, some of the updates on the progress of our partners' molecules through the clinic, and then I'll talk about our most recent aspect of this technology where we've added some capabilities and a little bit of hot off the presses preclinical data on that technology. Very good. Okay, this thing works. That's nice to see. There's different strategies, of course, to extend half-life in a variety of peptides and proteins. And we've taken this tack to add albumin, to fuse or conjugate with albumin. And we also take advantage of the recycling mechanism via the FcRn receptor, which is pretty well known. Albumin and IgG are recycled via the FcRn receptor, and this is where we attain half-lives, and I'll show you some data in a little bit that in the on peptides in the range potentially of equal to albumin or slightly shorter. But in general, the albumin-bound molecules are endocytosed. They're processed in that endosome via pH change. The detritus is separated out from the albumin and its payload, and then released back into the system for further use. There's a couple, so we've taken the albumin molecule and developed a really extensive suite of fusion capability with the albumin molecule. And of course, the native material that we manufacture is USP-NF recombinant human albumin. Also has the free thiol. It's identical to the sequence of human serum albumin, 585 amino acids, with a free thiol at cysteine 34. And that's been successfully used in the clinic via conjugation to GLP-1 analog. And we'll talk a little bit about that. We have two partners that have taken different approaches. Generally, our business model leans towards granting a license in a particular slice of a market, depending on the size of that market, et cetera, and that's all up to negotiation. But Conjugchem developed a conjugated version of their GLP-1 analog that has gone through phase 2 trials with once-week dosing. GSK is completed phase 3 trials and has put in the BLA for albiglutide. Launch is probably early in 2014. Both of these companies took the approach of putting a GLP-1 analog dipeptide onto the albumin. Either in the case of the albiglutide from GSK, that's a fusion, and then it's a conjugate using Conjugchem's their proprietary chemistry for that molecule. I'll talk a little bit about the half-life that we achieve versus the half-life of other extension technologies. This is information pulled from the literature. What we see is the FC GLP-1 analog with about half the half-life in serum as Albifuse, the fusion technology from Novozymes. Oh, I didn't quite finish this slide, but I wanted to make a point here this is a protein and not a peptide, but factor IX. We had some very nice results there, and it was pretty clear that the approach that CSL Behring was taking, using our technology with their cleavable linker, is very promising, and sorry for the lack of graphic there. And here's a comparison of the different types of half-life extension. Again, use factor 9 unmodified with the FC factor, factor 9 from Biogen compared to the AlbaFuse factor 9 from CSL. And we see significantly longer half-lives with the albumin fusion technology. There's a lot of work done on in addition, how might a albumin or albumin fusion help a formulation or an ME? And it's pretty clear that there's some of the benefits of albumin that albumin may confer in a formulation. For example, diminution of injection site reactions, some other reduction of immune response, reduction in aggregation, and quite a number of the benefits that albumin will confer also gets conferred on the partner when it's a fusion. I'm not going to stand here and read the slide. All this will be available to everybody, but there's a number of benefits that we see against other half-life extension technologies, and really many of them are really understood in the context that albumin, this is what albumin was made to do: carry proteins, peptides, and other payloads around the body. Now, the most recent twist on this technology is we've been able to modify the affinity of the albumin and of an albumin fusion or conjugate to the FcRn receptor by point mutation. And this is pretty well documented in the literature. There's a particular naturally occurring mutation that kind of, people did a lot of work on that. I can't remember the name of it right off the top of my head. But we then picked up a lot of IP with our partner, University of Oslo, around modifying the affinity via point mutation in the albumin molecule. And we can go up or down. So you'll see here that this is the wild type. And we've been able to modify affinities up. And then on the right here, you see this wild type. And we can modify down. And this is just looking at the difference in albumin half-life in our one of our mouse models. And you can see here that, oops, wrong button. This is native sequence albumin. This is a reduced binder. And this is an increased binder. We're seeing this difference in the half-life just of the albumin molecule without any conjugate or fusion. Here we've looked at the albumins in a transgenic mouse model. Now this was important for us to develop because there was, if you give albumin to a mouse, a human albumin to a mouse, there's going to be some immune reaction. So we've had to go to an engineered strain. And here's where we see differences between the, this is in the mouse, the half-lives of the various binders. And then we looked at a GLP-1 analog conjugated to the native material, and then the unconjugated material, and then on 2 different variants and the wild type albumin conjugate. And so here's the wild type at just about 12 hours. Here's variant 98 at 15, and variant 354 at 16.7 hours. Now, this is in the mouse model. Of course, there's quite a discrepancy between what we're seeing in humans as far as half-life of GLP-1 analog conjugates versus the mouse model because of the models. Yep. Of course, one of the main concerns in a modified protein is going to be the immunogenicity. We have a white paper available describing the immunogenicity work that we've done so far. We have 2 additional programs going to characterize the immunogenicity beforehand, and later this year and early next year we'll see in silico modeling and in vitro T-cell assays to predict the immunogenicity. We actually have done, of course, a lot of work on the material that's already in clinic and have a very high level of confidence that the modified albumin conjugates and fusions will show a similar reduction, similar lack of immunogenicity as the current products in clinic. And just this is our corporate color, and I'm going to have to tell them that it doesn't reproduce well in scenarios like this. It's actually a green color. But there's the business model working with Novozymes is, I won't say it's complex, but as you may imagine, there's some history in licenses, but we've attempt to make it as straightforward as possible. We have an expression system, Saccharomyces cerevisiae. It's a GRAS system, and we've been using it for years, and we really like it. And so we can license the technology to be used in our expression system, or our partners have also been successful at expressing our fusion proteins in E. coli and mammalian cells, CHO cells. So those are all available as options additionally. And just in summary, the modified sequence albumin allows long half-lives, proteins or peptides, and of course there's flexibility in design because there's a number of mutations that may confer benefits. The chemistry of conjugation is relatively straightforward with the free thiol malamide reaction. It's the expression system, if you're expressing it, makes a pretty easy to manufacture drug. And as I mentioned previously, there's a lot of benefits that albumin brings to the party that, in addition to half-life extension. And with that, I think we're done. Thank you very much.